Hello, everyone. So in this lesson, we're going to be reviewing our rational zero theorem. We briefly started an example, but we didn't fully get through it. So we'll review what it means. We'll just do it on the calculator just to visualize what it tells us so that we can just see exactly what it tells us and that it makes sense, that it's true. And then later on, the main part of this lesson is we'll be combining our rational theorem with our synthetic division, our factoring, and the other things we know about polynomials to be able to find all of the roots or zeros on our own without having to be told to factor, without any hints or any calculators, just being able to get all the roots and the features so we could do have an accurate sketch of what the graph looks like, once again, without needing any technology. So remember, our rational theorem tells me if I list out all the factors of the constant, so whatever my constant is here, and divide by the factors of the leading coefficient, because when we did all our factoring, we said that's really where our factors come from, is we see what factors of the constant usually adds to the middle, or grouping that constant is important. And even with payback, that leading coefficient does have an effect, especially with quadratics there. So if the polynomial's roots are rational, it would have to be in this list that we create using these factors. If it's not in this list, there are two other possibilities. So if you actually see it on a graph, even if you have like a cubic, so if you see it and and only one of them are the nice whole numbers or fractions that you come up with, that means the other two would be irrational. So remember, those are the decimals that go on forever. Or if you don't see it at all on the graph, or if you only see one of the roots, the other two would be imaginary. So if it's not in this list, that means they're irrational if we see them, or if we don't see them, they would be imaginary. So if I look at this one, the one we started, so we listed the factors of 6, so 1 times 6 and 2 times 3. And the factors of 1, my leading coefficient is just 1. So if I divide all these by 1, I just get the same thing. So that tells me if the roots are rational, we could quickly type this in. If I look at the graph, it does look like it hits 3 times, so all 3 are real. So if they're rational, it would have to be one of these. So you could check it. I think this one was 2 back. So if we check the table, -2 was in fact one of the roots. So -2 does give me an output of 0. So that was one of the roots. But if you look at the table back from -6 to +6, since that's our highest number, none of the other roots, you can see where it goes from negative to positive. So somewhere after 7, it goes from negative to positive. You can see here at 7 point something, it goes from negative to positive. But we don't have any fractions or decimals on this list. So that means that root, as well as this one, sort of between 0 and 1, would be irrational. And you could do second trace 0, it comes out to be like 7.0412. It's a decimal that goes on forever. So at this point, we could just say the other two are irrational. Okay, so you could, like I said, you could use second trace 0, or if you use synthetic division to divide this, you could get it down to quadratic, and then maybe you could use a quadratic formula. If it's even, you could try completing the squares. There, you could algebraically find it, but at this point, we'll just classify one rational, that's the -2, and the other two would be irrational. So let's take a look at this one. So I'll stick with my color scheme here. So my constant in red here is 15. So we would list out all the constants of 15 in our numerator. So it looks like we have 1 times 15, and then 3 times 5, right? So 3 times 5. I like listing them in order. So I recommend you do the same as well. And then if I look at my leading coefficient, it isn't 1 here, it's actually 2. So that's leading, the factors of that will be 1 and 2. Okay, so if I list these out, so I have 2 things. So I have to divide everything by the 1 and divide everything by the 2. So if I divide everything by 1, it's just going to be the same. 1 divided by 1, 3 divided by 1. So it's going to be the same 1, 3, 5, 15. Okay, but if I divide it by 2, 1 divided by 2 would give me 1/2. That's a possibility. If I divide the 3 by the 2, that would give me 3/2. Once again, plus or minus for everything, because I don't know, signs are different. I don't know which one's which. 5/2 is another possibility, and then it looks like 15/2, right? So if I divide all 4 by 2, so these are all my possible roots. So if the rational roots, so if the roots are rational, it would have to be in this list. If they're not, they're either irrational or imaginary. You could check the graph. So let's do this graphically. So I'm going to go ahead and type this in. I recommend you follow along as well. So if I type in the 2x cubed plus x squared minus 16x minus 15. Okay, so just a quick look at the graph. Once again, we'll be doing this algebraically without technology in a moment. So we're expecting it's a degree 3, so we have 3 roots, so all 3 are going to be real, so no imaginary here. So I recommend checking our table. You could kind of see that might be like a -1. So let's check our table here. So it looks like, okay, 3 is 1 root. That is -1. So we have -1. We have 3. Okay, I don't see the other one just by going up and down, so I don't think it's in the table, but if we go back to the graph, you should be able to get an idea of where it is. So if we go to the graph, so there's a -1, there's a 3. So it looks like it's gonna 1, 2. So it looks like it's between 2 or 3. So -2, 3. So if I look at my roots, it could be -2.5. Because if I look at this root here, this would plus or minus, this is 2.5 basically, right? So you could do second trace 0, or these are basically going by halves, right? This is 0.5, 1.5, 2.5, what was that, 7.5? So what you can do is we go to your table settings, so table settings in here, rather than going by ones, you could go by 0.5s just to get those halves in the table. And we said it looked like it's -2.5, so I could start in the negatives here, so it doesn't matter. So anywhere in the negatives, that's your starting value. So if I go back to my table here, now it's going by 0.5, so it does look like, so there's a -1. It does look like -2.5 is your roots. And once again, you could do second trace 0, but negative, so that's 5 halves. So -5 halves. So all 3 roots here are indeed rational. So those would be the 3 roots. Okay, so our list does include all of the roots. So if they're not irrational or imaginary, they would have to be in this list, basically, is what this theorem tells me. Let's do one last one just to get a little bit more practice here. So this one's a little bit of a larger one because my constant here is 30. Luckily, my Q is 1, so I don't really have to. So the factors of 1 are just 1. But when I'm listing out the factors of my constant, so we have 1 times 30. We have 2 times 15. 3 times 10. And then we also have 6 times 5. So you could just go in order as long as you're proficient. I like, just since this is our first one, so 5 times 6, so 5 times 6. So it looks like those are all my possible factors. Okay, and if you divide by 1, you could just basically write this same list out here, because dividing by 1 will just give you the same thing. So these here are my possible factors. For the sake of time, I won't write out, but you should write out that same thing over here. Okay, so if the roots are rational, it would have to be in this list. Okay, so let's go ahead and type this one in to finish this off, and then we'll relate this back to our synthetic. So x to the 4th plus 3x cubed minus 7x squared plus 9x minus 30. Okay, so if I go to my graph, it looks like it only hits twice. You could zoom out rather than going 10 by 10 if you want to just look at 20 by 20. Just make your grid larger just to get a bigger view, just to show you that in fact it only hits twice. If you zoom out, it only hit twice there. I'll go to zoom standard, just go back to my 10 by 10 view. So it looks like 2 of the roots are real, but we're expecting 4 roots here, right? So that means the other 2, if I don't see them, would have to be imaginary. Okay, so for the other 2 roots, let's see if they're rational. So it would have to be in this list. So you could check the group table here. So I'm still going by point. Let me go back to my table settings. We'll just go back to going by ones here. So changing table by ones. Okay, so let me check. So there's one of the roots, so x equals 2. That's in our list, right? So 2 is a possibility here. Okay, we have all the way up to 30 to check. So if I go back, so it looks like -5 is my other one, which is also in our list. So these 2 are in fact roots. So -5 and 2. Okay, so 2 roots are rational, 2 are imaginary. Okay, so let's go ahead and put this together. So finding roots algebraically using our theorem here. Okay, so normally I would give you a factor, then you do synthetic division to break it down, and then factor normally to find the roots. So this time I'm not telling you a factor, but now that we have a rational 0 theorem, what I can do is I can list the possible rational zeros And then we could just use synthetic division to check until we find one that goes in. Now remember, our remainder theorem tells me, or sorry, our factor theorem tells me if I get a remainder of 0, that it is indeed one of the factors or the roots. We just have to search for one of the factors. Okay, so let me list the possible. Okay, so the possible rational roots here. Okay, so the factors of the constant are just going to be plus or minus 1 and plus or minus 3. Okay, then my leading coefficient is just an invisible 1 here. So just plus or minus 1. So it looks like my possible roots are either 1, -1, 3, or -3. So those are the only possible roots. If they're not here, they would have to be either irrational or imaginary. So if I'm asking you, if you're asked to find the roots algebraically, it's going to be one of these. So we just have to check until we find one. So usually I just start with 1 because it's easier. Then I'll check like -1. So if I check 1, we could quickly check within synthetic. So 1, 5, and 3 are my coefficients. So we could quickly check with synthetic if this is a factor. So we'll bring down the 1. Okay, so 1 times 1 is 1. 1 plus 1, 2. 1 times 2 is 2. So -5 plus 2 is a -3. 1 times -3 is -3. So in fact, we do get a remainder 0. So we're lucky on our first try. So it looks like 1 is a factor. So that means 1 is a root. So x minus 1 is the factor, right? So x minus a, whatever my a is. So we have, so we've just found one of the zeros. The 1 goes in evenly. Okay, so with what I'm left with what? X squared plus 2x minus 3. Okay, so set it equal to 0. So I think we should be able to factor this more. So factors of 3, so signs are different, so plus or minus. So I needed 2, so 3 minus 1 gives me a positive 2, so 3 minus 1. Okay, so it looks like my other roots are going to be -3 and then positive 1. Okay, so I need to tell you that x minus 1 was a factor. You can just check 1. And then once you find one that hurts, we got lucky, you did it on the first try, but you could, once again, you might not get lucky. If I started with -1, for example, I'll bring the 1, 5, -5, 3. You can check, you bring down the 1, this would give you 1 times, so that will give you -1, so that's 0. That times 0 is just 0, -5, and -1 times -5 is positive 5. So this will give you a remainder of 8, so that would not be 1. So you just go use synthetic until you find one. If these didn't work, try 3, try -3 until once you find one, you can get the more broken down version, which you should be able to factor. So these are going to be my 3 roots. So all 3 are rational and real. So, all right, let's do one more together. So let me divide this up. Okay, so here, my constant. So if I list my possible zeros, so my possible rational roots here, or rational zeros. I'll say 0 since it's a rational 0 theorem. So factors of 6 would be 1, 2 times 3. 1 is for everything, right? And then 1 times 6, so 1 and 6. Okay, and my constant here, my leading coefficient rather is 2. So not 1 here, so 1 times 2. So those are the factors. Okay, so just like the one we did before, if I have to divide these all by 1. So if I divide these all by 1, I'm just going to get the same thing. So I'm going to list those out. Okay, and if I divide these by 2, so divide each one by 2, so 1 over 2, I have to add that to my list, 1 over 2. If I divide 2 divided by 2, 2 over 2 is 1. We already have plus or minus 1 in our list, so I don't need to list it again. So 2 divided by 2 is 1. We already have that. 3 over 2, I need to add to my list. Okay, and then 6 over 2, 6 divided by 2 is 3. We already have 3 in our list. Okay, so it looks like we have 6 possibilities and then plus and minus, so 12 possibilities if you consider both the positive and the negatives. So these are all the possible ones. Okay, so I just need to check until I find one that works. So we can start with the 1 again. So let's see if we get lucky. So we have 2, -3, -11, and 6. And hopefully once you get more practice with synthetic, it becomes more just quicker as you go. Okay, so 2, 1 times 2 is 2. -3 plus 2 going down is a -1. This would give me -1, which is what, -12. Okay, so my remainder here is what, -6. So either way, that doesn't work. Okay, we could try -1. Same coefficients. Bring down the 2. Okay, so let's do this one. So -1 times 2 is a -2. That'll give me -5. -1 times that will give me a +5, which is -6. It almost looks like it, but -1 times -6 is a +6. So this is going to give me 12. It almost looks like this cancels, but not quite. So this one is also no. So you could keep going with 2 and then do -2, but for the sake of time, -2 is one of them. So if you try 2, it won't work. So move on to -2. So once you get here, you should get the remainder of 0. So bring down the 2. -2 times 2 would give me a -4, which would give me a -7 here. -2 times -7 is a +14, which gives me 3 here. -2 times 3 is in fact -6, which does give me the remainder of 0. So you find the first one. Okay, so if -2 is the root, that means the factor would be x plus 2 to get me the -2 once you set it equal to 0. So I'm left with here, what, 2x squared minus 7x plus 3. Okay. Okay, so we already know this is -2. So we found one of the roots. And once again, it's cubic again. So we're expecting 3 zeros. So we have 1. We found that was synthetic. That was in our list. The 2. So this one, not as nice as the last trinomial. There's a 2 in the way, so we'd have to use payback in order to factor this. Usually you'll get a nice either difference of squares or trinomial with these, but sometimes you might have to do payback, or if it's not factorable, you might do quadratic formula with this, completing the square too. But you should be able to find the roots. And once again, these are going to be in, if they're rational, which they are, if it's factorable, this one is, it'll be in our list. We could check that they're in our list as well. So let's pay back here. So I'll do 2 times 3, which is 6. Okay, so factor normally, just keep the 2 in each group. Okay, so it's factor normally, so x squared is x times x. Signs are the same, positive, so they're both going to be negative. Okay, so factors of 6, that can be negative. So -6 and -1 add to -7, right? But we did the times 2 here, so we have to pay it back. So I could take it back from this group. So it looks like this will give me what, x minus 3 with this 2x minus 1. Okay, so it looks like this root also comes for free, so x equals a +3. So there's my second root, and then if I set this equal to 0, I could add 1. So this will give me 2x equals 1, divide by 2, so x equals 1/2. Okay, and if you go check, you can even continue doing synthetic. If you know the other roots are rational, you could check 3, that'll give you a remainder 0. So you could kind of find all of them, these 2 roots with synthetic, but this one you won't, you can't do. I mean, you could do it with fractions, but you don't want to really. But 1/2 was in our list, right? That was one of our possible zeros. So it looks like 1/2 was one of the zeros. What do we have? -2 and 3. So -2 and 3. So all of the roots were indeed in my list. So this theorem tells you all the possibilities. And once again, if they're not, it might be irrational. You might have to use quadratic formula. You might get a radical 7 or something that's irrational. Then it won't be in your list. But if they are rational, it has to be one of these, what do we say, 12 possibilities. So the 6 positive versions here, the 6 negative versions. Sometimes you get lucky, you get it on the first try. I usually start with 1 or -1. Sometimes it might take you 3 or 4 or 5. But once you get that remainder 0, you could break it down. And just keep breaking it down and factoring it until you get the zeros here. So that'll be that one. If you want one more to try, there it is here. Sorry, I got kind of covered there. That should be a +12. I got erased there. So if you want one more to try, just an extra example, try that one. But on the sheet, I want you to practice. So if you go to the sheet, so basically on the backside, it's a rational theorem. So this one, you're just listing the possibilities and then using the calculator, which we did to see which ones are in fact zeros, and then classifying the other ones as either rational or imaginary. But you also have 12 examples here of finding the zeros on your own. So list all the possibilities and then use synthetic until you get one. These are pretty much all cubic except the last one. So once you find the first zero, break it down, you should be okay. You don't have to write 60. There's a lot of factors. You could use your calculator. You don't have to write it twice. Once you write it for this one, for number 12, you don't have to write it again. But yeah, you have a practice with the rational zero them here. So listing the zeros, just checking the calculator and using synthetic to actually find the zeros. So go ahead and practice on those as well.